Okay. So let's see the primary bonds. Okay. For the primary bonds, actually we can divide it into three lah. Okay. Ionics. Ionic is mostly on the metal non-metals. Okay. So especially ionic bonds, for example, like an ACR, right? They also metal like from the group 1A can transfer the electron, and Cl from group 7A can accept the electrons. Okay, so it's more to the electron transfer. Okay, between group 1A 2A to group 7A and 6A lah. That's the example. And second one is the covalent, non-metal with non-metals. Covalent bonding is um, mostly on the sharing electron. Okay, so example like Cl, okay, or ClBr. So that is more on the sharing electron. Okay, so they can form a covalent bondings. So we can distinguish this bonding based on the difference in the electronegativity. Okay, since from the predictables we can know the electronegativity. So based on the difference in electronegativity between elements, so we can know what bonding they can form between elements or atoms. Okay, and then for the metallic bonds, metallics is between metals is mostly is not really like a bonding, is more to the C of the electron or electron pooling. Okay, so like sodium, right? Okay, so with the C of the electrons, so especially metallic bond, it can conduct electric. Okay, so we have to be careful with this metallic bonds. Okay, so let's see. This is the examples of three models of the chemical bondings. As I explained, this is ionic solid. Okay, electron transfer and then electron sharing, ClBr. This one. Okay. So and there's a sea of electron. Metal ion cause in the sea of electrons. Okay, that's why, because this electron is moving. That's why they can conduct electricity. Compared to ionic bondings in solid state, ionic bonding cannot conduct electrics. Such as the characteristic of the ionic bonding is more to a brittle like a ceramic. There's a difference. Okay. Okay, so for the ionic bondings, okay, as I told you that electron transfer from metal to the non-metals, okay, the result is if you can see, they try to complete the outer shells, okay, like noble gas, on the we want to achieve the octet state or stable, okay. So for example, like 1A, 2A, and also this is a reactive metals, and also 6A, 7A. Okay. So when metal lost its electrons, it can form the cation. When the non-metal accept or gains the electron, we call it as an ion. So the radius for the cation is going to be reduced, while the anion is going to be increased. Okay. Okay. Yeah, this is the explanations. If you look at here, that the electron can transfer, okay, complete outer shells, lose electron, cation, and ion. So the bonded together, we call it as a Coulomb attraction force. Okay, so this is what we call it as the attraction force to form the ionic bondings. So if you look at here, this is the example of the uh, how sodium chloride, the bonding between sodium chloride. If you look at here, that actually all right, if you look at here, that now this is quantum number n equal to 1, this is quantum number n equal to 2, this is quantum number n equal to 3 lah. The outer shells 2, 4, 6, 8. Okay, so if you still remember, it's gonna be 1s, 2s, and also 2p lah. 2p. 2p should be this side, and also this side. Okay, we still remember. So this one can fill with 6 electron, 2s, 2 electron, 1s, One S is a one electron, two electron. Okay, two, six, another one, this one. Okay, additional one. Two S, two, one S, two S, two P. Okay, three S. Okay, so three S, one electron. Yeah, three S, one electron. So look at here that this one can transfer electron to the chlorine. Okay, chlorine atoms. Since they have a vacancy on the, how to say, if you write in orbital diagram, there's a vacant in there. Okay, that's why it's 7, because cannot achieve the octet number, right? So once we transfer, they can be in octet number, a stable state. Okay, so when we transfer, it's become 288, 288. Okay, so the radius increase, this one reduce, the decrease. Okay, so easy, right? Okay. Use partial orbital diagram and Lewis symbol to depict the formation of sodium and oxygen ions to the atoms and determine formula of compound form. Do you still remember orbital diagram? Can you do, and please paste in the Jamboard. Let me give you the what is it? The links. Can you do? Takes one paper. Okay. So please do partial orbital diagram and Lewis symbol if you still remember. Just recall back. Jamboard. SETK2243. Page 4. Page 4. So this is the Jamboard. So please go to page 4 for the Jamboard. Okay, please paste your answer. Okay, so if you still remember partial orbital diagram, partial. Depict the formation of Na plus and O minus. Okay. So partial orbital diagram, this one. If you still remember. For example, like lithium fluoride, right? Okay, this one lithium. For example, this one lithium. I just give example, okay? This is the lithium. Lithium 1s, 2s, and then 2p. This is a partial orbital diagram. Okay, plus with fluorine. 1s, 2s. Okay, so fill this one up first. Okay, this one, this one, this one, this one. Okay, this one, this one, this one. Okay, to form lithium fluoride, so lithium plus this is example, but you have to do for sodium oxide. Okay, and then F. This one is lithium fluoride. If Lewis symbols, Lewis symbol macam ni lah. Lewis symbol ada one atom, right? Plus 1, 2, 3, 4, 5, 6, 7. Okay. So this one transfer electron here because there is a vacant here. So lithium. plus plus chlorine. This is Lewis. This one orbital diagram. Can you do for the NaO2 minus? Can you do? I give you 5 minutes. Easy, easy.
Na2O.
Na2O, yes. Na2O. Of course lah, Na2O. So, but I told you you have to use a partial orbital diagram and Lewis symbol to depict the formation of Na and O2 minus. Orbital diagram, Lewis symbols. Can you show in the Jamboard? You can sketch in the A4 paper and take the what is it? Take the picture and paste in the Jamboard also is possible. Nobody. Hmm? Siapa yang tulis ni? Ada seorang yang tulis.
Doctor?
Yes.
So we write the orbital diagrams for each of the ions.
Yes, yes.
Okay.
Okay. The formation of Na plus and O2 minus. So you have to draw lah. Kalau saya 45. Siapa lagi tak ada group ah? Anyone already have a group? Apa hari tu lupa lah saya. Seorang tak ada group. Seorang lagi tak ada group. Apa yang mesej saya tu? Amirah bukan Amirah. Hmm? Hmm?
Doctor?
Yes.
So initially, Na has 3s1,
Issued
right?
from atoms. From
So
the
it
atoms.
has 3s1. Also, it gives that 3s1 to O
What do you think?
form. So do we draw an arrow of the movement of
Huh?
electron, or do we just draw for
No,
the ion?
if for nitrogen, for
Just complete
sodium,
for the ion.
the complete the ion. Just make the pathway. The pathway. Draw the pathway. What's this one? Okay, the one who draw here, the one who took the picture, right? Lewis structure. Yeah, just like a Lewis structure, this one. This one is the correct. But how about the partial orbital diagram? You just give the the what is it the the orbital diagram for Na plus and O2 minus, right? So I think you should start from the beginnings lah. From starting from Na and also oxygen. Okay, for the partial orbital diagram. Okay, it should depict the formation of Na plus NO2. So meaning that should start from the 2Na for the partial. I think for the Lewis structure already have answer there. Okay, Na. I just started with the 3S. Okay, this one. S. Okay, plus with O. This one is just start with the 2S and 2P. Okay, and you can get this one 2Na and plus O minus. Okay, so meaning that okay, so this one is for O2 lah. Similarly also for Na. One S, 2S, and then 2P. Okay, just fill. You fill lah. Okay, fill this one. Difficult to draw. 1S. This one is starting from 2S now. 1S is already there. This one is 2P. 1S, 2S, 2P. This one. Okay. Okay. Just recall back. Have you learned? Oh, it's already 25 minutes. Okay, so thank you. Okay, let's we move to the what else? The ionic arrangement. Okay. For the actually for the ionic bondings, the ionic arrangements is later we will discuss in detail in chapter 3 actually. Okay, if you look at here is this is in 3D dimension, the ionic compound. Okay, so like a CSCl, this one the bottom part there's the dot one is the unit cells. Okay, because there's another unit cell at the center, we call it as a centered cubic unit cell. The formations we call it that one. This one is there's a we call it as a face centered cubic unit cell. Okay, there's a four type of basic unit cells. The arrangement, they have a simple cubic unit cells, body centered cubic unit cells, face centered cubic unit cells, and base centered cubic unit cells. This is the basic types. Okay, from this basic type, we can get around we can divide it into 14 types of unit cells. Okay. For example, like a cubic unit cells, it can be divided into 3, tetragonals can 2, and so on. All this in 3 dimension. Okay. Later in chapter 3, we will discuss in different type of the unit cell, the arrangement in 3D. Okay. So this is important to see the vacancy or how many atoms inside the unit cell. Okay. So that is regarding on the arrangement of the ionic cells. Okay. Okay. Uh, Okay, for the atomic already, as I told you, what is it? Alkali and alkaline earth metals transfer electron, the radius decrease, while for the 6A and 7A increase the size of the radius. So it's general, right? So ionic bond formation, if you look at here, that is based on the electrostatic attractions. Okay. Uh, So sometimes in crystal, okay, is a brittle, the characteristics, okay. Actually in solid form is a neutrals. They cannot conduct the electricity, okay. But in molten state or in liquid state, they can conduct electricity lah. Okay. So the basic ionic packing arrangement, if you look at here, that fixed in its location in the crystal lattice. Okay, as I told you, they are arranged in the four basic type of the unit cell. Okay, so the other one, the others you can read. Okay, just the basic. Okay, so in terms of the bonding energy, okay, in terms of bonding energy, if we look at here that the lattice energy decrease as the size of ion increase. So meaning that moving down to the group, so daripada from the top to the bottom. Okay, because the electron is become farther away from the nucleus. Okay, there's less attraction energy from the nucleus. Okay, and there's another factor, we call it as shielding factor. Okay, that's why the energy is become decreased. Okay, so lattice energy increase significantly when ion involved have higher ionic charge, like +2 much higher than +1. If you look at here that we compare with the magnesium, right? The energy, right? The melting, even we just compare with the melting, right? So we need the high temperature to melt the magnesium oxide as compared with the lithium or other metals. Okay, so that's important. Okay. Okay, so this is the material properties. As I told you that have high melting temperature. Okay, because possess a large bond energies. Okay, electrical conductivity actually is not conduct electricity because it's very tight. Okay, it's very tight, so the electron cannot moving. But once you make it in melt or dissolve in the water or in the molten state, it can the ion can free, right? It can moving. Okay, so this can conduct the electricity. And chemical analysis is stable. Okay, because it's achieved the octet state like aluminum oxide and silica oxide. Okay, so this is the picture showing that uh, how the ion bondings, the compounds in ionic forms can conduct the electricity in molten state as well as dissolve in water. Okay, so this is the characteristic, the main characteristic if you compare with the non-metals. Okay, okay, and in terms of the mechanical properties, as I told you, it's hard, rigid, uh, if it's very strong, like a glass ceramics. If you, how to say, if you uh, using the hammer, right? You hit with the hammer, it's gonna be cracks, or it's a very brittle. Okay, it's gonna deform little, but it's a fracture. Okay, so this is the characteristic of the what is it, the materials which have the ionic bondings. Yeah, this is the explanation. You can, okay. So look at here that the crystal is cracked. Okay, it's just a deform little, but mostly is a fracture. Okay. Okay. Any question about the ionic bondings? Easy, right? Okay. To the difference between ionics and covalent, we can distinguish, differentiate mainly based on the electronegativity uh, difference, electronegativity difference, delta En. Okay. So we can know which element can form the covalent bonding and which element can form ionic bonding as well as metals. Okay, based on the difference in electronegativity. Okay, because in predictable we can get the electronegativity. Okay, so you can calculate between six element in 6A and 1A, right? So you can calculate just minus electronegativity for 6A and 1A, or 7A with a 2A. So just subtracts, so you can get a difference in electronegativity. Okay. Okay. So that is about the ionic bondings. We will move to the covalent bondings. I hope it's clear about the ionic bondings. The the properties. Okay, and then in terms of the size. All right. So I hope that you can understand in terms of energy. Is it clear? Okay. Okay, so we move to the covalent bondings. Okay, covalent bondings, as I told you previously, is of pairing the electrons. Okay, bonding pair or share pair lah. Okay, so usually is the electronegativity is really close, okay, close by in the periodic tables. Okay, it can occur between non-metals. Okay, also possible in ionic and metallic solids. We call it as a mixed bonding lah. Okay, there's a we call possible mixed bonding ionic and metallic. Okay, but mostly the easiest example is non-metallics between non-metal. Okay, 6A 7A. Okay, the same if you look at if you still remember that ionics we transfer the electrons, okay, to the vacant orbitals, but for the covalent we sharing or we overlap the orbitals. Okay, so for the most the exact example is like hydrogen lah. Okay, the simplest molecules, this is very strong. Okay, so this is a examples. Okay, I don't need to explain, this one already explained. Okay, hydrogen, right? So they are sharing the electron. Okay, so this is a highest probability of the finding bonding electron is overlapping area. Once they bond together, sharing the electrons, they will be in the stable state. So at that time we can calculate the length, the bond length of the electron lah. Okay, so the length of the uh, H2 bond, dia punya bond length lah untuk for this hydrogen lah, because it's not when the sharing the electron is already in how to say a stable state. Yes, a stable state. Okay, so this is about the covalent bonding. Okay, so if you look at here, this is an example of the explanation about the hydrogen bondings, how to calculate the bond length for the hydrogen bonding. Okay, if you look at here, that nucleus of one hydrogen atom attract the electron cloud of the hydrogen atoms. Okay, after and nucleus repulsion becomes significant, meaning that when they attracts and then after they share the electrons, the repulsion energy and attraction energy is become neutrals. Meaning become equilibriums, not neutrals. Equilibriums. Okay, so this is the in equilibrium lah. Okay. Kalau you buat derivatizations, is become zero. dy over dt, right? dy dx is become zero. Okay. Kalau in term of gives energy is also is become zero because in equilibrium. Okay. 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 So meaning that equilibrium point where attraction force are balanced against repulsion force. Okay. So we can calculate this hydrogen bonding. Okay. So this is another example, the picture. If you look at here, the bond length of the hydrogen is about 74 picometer. Pico is times berapa? 12 negative 12. Negative 9 nano, negative 12 I think. Okay, pico. Much smaller. Okay, it should be in equilibrium state if you want to calculate uh, the bonding of a hydrogen molecule. Okay. Okay, so if you look at here that distribution of electron density, if you look at here that repulsion and attraction is in equilibriums, that's why it's similar, right? But if HCl's, the electronegativity is going to be to this side. So your graph is going to be much higher. This is negative, this is positive. Because there's a dipole moment here. Okay, this one is the same, right? That's why you can see the graph is just the same. Okay, positive, positive. Okay, so another example is a Cl2, O2, N2, okay, with the p electron at the outer shell. Okay, so if you look at here, this is examples. Okay, they are sharing the electrons, one electrons. They become the opposite state, single bond. Okay, so this one is a covalent bonding for the diatomics, and also with the what is it, double bond and triple bond. Okay, oxygen and nitrogen. Okay. Outer shell is this one. If you look at here, that 2p, right? and then this one is a 2p4. So when they're sharing, we can get double bond 2828. So also 288 because outer is 3, right? Okay. There is a lone pair. Actually, lone pair is very important in determining the arrange geometry of your atoms, like a water. Okay. If you see, water have a lone pair. Okay. If you look at based on the observation, just based on your observation, the geometry of water is like a linear, right? Okay. H the geometry. But since there's a electron uh, lone uh, lone pair of electrons, the geometry is not linear anymore. Okay. So you have to know this one, the geometry. Later, I'm not sure this slide I will explain on the geometry. It's important in determine the geometry. I think so we will cover a little bit about the geometry, I think. The structure. Okay. So this one is not a linear anymore because there's a force. If you look at here, that actually is not something like this. It's more like this actually, the lone pair. Okay. So there will, how to say, push this bonding actually. So it's not become linear anymore. Okay. So when they push, the geometry is not linear anymore. So it's become, kalau yang paling senang macam ni lah. This is a double the geometry. Hydrogen. So this is in the tetrahedral punya shape. Okay, the geometry is become tetrahedral, so not linear anymore. Okay, I think we just cover some part about the geometry, the structure of diamond. Okay, so it's important the lone pair actually. Okay, so let's see the non-polar versus polar covalent bonds. Okay, we can know whether the element can form ionic bondings, polar or non-polar covalent bondings. Okay, look at here that for pure non-polar covalent bondings, okay, the electronegativity difference is 0.520, no dipole, meaning that like a hydrogen, nitrogen, and fluorine, F2. Okay, but polar covalent bondings have significant electronegativity difference. If you look at here, that 0.522. Okay, so they can form the polar covalent bondings. Okay, like HBr, okay, HF, that one is like a high polar covalent. Okay, this one non-polar is 0, fluorine. Okay, because the same electronegativity. Hydrogen, I'm not sure what how, uh, from the predictables. From the predictables, the electronegativity of the yeah. For example, fluorine 3.98. Okay, so we get here 3 of fluorine 3.98 minus 3.98 is equal to 0. But for HBr, if you look at here, hydrogen is 2.20, and then Br, bromine, which group 2.96. So if you look at here, that electronegativity difference is around 0.676. So it's polar covalent. It's between 0.5 to 2, right? But more than 2, okay, like this one, and it is become ionics. Okay, so mostly is if 0 to 0.5, 0.4, that one is the covalent bondings, non-polar. 0.5 to 0, 0.5 to 0, okay, and then 0.5 or 0.4 to 2, 1.9, okay, that is mostly polar covalent bondings. And then 2.0 to 3 or 4, okay. I don't think until 4. I think around 3, 3.5 something. That's going to be, the bonding is going to be ionic bondings. Okay. Okay, because they have a very large difference. Okay, they can form ionic bonding. Okay. So if you look at here, that this is like more to negative. There's a dipole moment. This is pure. Okay. Okay. This one is the, how to say, the picture or uh, the character, the range, okay, the range of the mostly between the covalent, okay, polar covalent, and then ionics. Okay, you can see here that the green color is become mostly ionic. This one is polar. Okay, so this is the measurement. So if we compare with the electron density, okay, as I told you previously, equal sharing electron, this one hydrogen. Right? Fluorine also sharing non-polar. But for hydrogen fluoride, a little bit, this is more to negative, right? The attraction. Okay, this one compare. This is unequal. Okay. So the electron density shift to the fluorine. Okay. Okay. Easy, right? Okay. So let's say we the bond order, okay, bond order as well as bond length, bond energy, the dimension. I think you know already. Bond order is a number of sharing pair, especially for the covalent bonding. Whether you want to because whether the bonding is a double bond or single bond, so we can measure in terms of bond order, bond energy. How many uh, uh, the energy that required to dissociate the bond length, okay, or overcome the attraction force, okay. We call it, sometimes we call it a bond dissociation energy, BDE. We just make it short, BDE, dissociation energy lah. The energy required to dissociate to cleave the bond, okay. And then bond length is the distance between nuclei to bonded atoms. This one already discussed. Okay. So yeah, this one overcome the attraction force, for bond energy, number of shared pair, bond length in distance. And then we look at here that the relationship between the bond order, bond length, and bond energy. So bond order higher, bond length decrease, meaning that bond energy decrease. For example, this one, triple bond, right? Bond order, they have a three pair, right? Three pair, share pair, three. So energy is higher compared to double bond, and the length is become shorter, okay, compared to the double bond and single, okay. So meaning that the energy to cleave the bondings, the energy required to cleave the bond, okay, is depending on the bond order as well as bond length, okay. Okay. So yeah, this is the electron configuration. I think so, you know, in terms of the uh, orbital diagrams. This is ground state arrangement. Ground state arrangement is at the lowest energy lah, at the lowest energy. Get here that. But when they absorb photon, for example, if the atoms or the electron absorb photon, for example, they absorb photon, right? This one, 2s. They are getting excited, so they can jump to another orbital. We call it hybridization, this one, okay. But 2s can jump to 2p and 2p can jump to s, but cannot for 2p they cannot jump here, okay, they cannot jump here between the 2p, okay. You have to remember that is the rule actually, okay. So between 1s 2s to 2p is possible to jump, and 2p to s is possible, but they cannot jump between 2p. If you look at here, 2p is a x direction, y direction, and z direction. Okay, if you still remember, p is this. I'm not sure. This one is z. This one is y. This one x direction. Because since um it's a dumbbell shape, right? Okay. This is a z direction. This one is y direction. Okay. Actually, the how to say the localization of the electron for each axis actually is similar. Sometimes the electron is moving to the z direction, and then sometimes go to the x direction, sometimes go to the y direction. They are moving actually. Okay, that's as previously as mentioned, they are not exactly evolve around the nucleus actually. Okay, there's a we call it electron density, right? Or we uh, uh, what I told you last time, a cloud of electron. Okay, is to locate the electron is we have to use the amplitude, or in chemistry we call it a wave function. Okay, because they can amplitude the electron. Okay, but if for 1s to s is easy. 1s to s is just a this one, right, round shape. So the two electron is just localized inside this round shape. Okay. Okay. Uh, can you do this example? Use a polar arrow to indicate the polarity of each bond NH, Fn, and ICl. Rank the following bonds in order by increasing the polarity. And please justify this one. This one B. Sorry. YA. This one should be B. Can you do? And paste in the Jamboard page 5, okay? Page 5. Use the okay, polar arrow is this one, okay? I think you still remember this one. This is the polar arrow. I like this one. This is polar arrow. Okay, I give one example. Example 5. For example, like this one. Right? So you have to see the electronegativity. Please refer to the predictables. Maybe you can search from the Google's predictable electronegativity. Okay, see the electronegativity first. Okay, so you can know to which direction that arrow. Okay, that indicate the polarity. Can you do and paste in the Jamboard? For example, look at here, and what is the electronegativity? H, F, I, Cl. For example, nitrogen, the electronegativity is 3, and then H is equal to 2.1. Okay, this is much larger, right? So meaning that N, H, so electronegativity is to this direction, the polarity. Okay, please do. I give you 5 minutes, almost finished. I thought today we can finish, so we have to continue on the next class. Tomorrow, right? Okay. How about F and I and Cl? Please do. As well as B. Rank the following bonds in order of. So this one you have to calculate the electronegativity difference, so that you can rank which one is have a higher energy as compared with the this as comparison, which one have a higher energy. Please give you 5 minutes before we stop. Anyone? Nobody?
Doctor.
Yes?
So Fn is towards F.
You have to write in the Jamboard.
I don't. I think I lost the link, Doctor.
The
The
same.
Jamboree.
The chat box. Yeah, I give you. How about other student? Polarity HC, HN, HO. Okay. How about what is the justification? There should be this one, okay? There should be not only arrow, but this one. Okay, and this one. Hmm. Okay, okay, okay. This one okay. That LCM is okay. NH. Who did this one? Can you revise? Okay. Okay, that one is okay, okay. Okay. Thank you. We have answer already. think that's good. Okay. You can access the Jamboard anytime. Okay, to see the answer. Do not worry. Okay.
So,
So
doctor, the more polar means more stronger bond, right?
what do you think?
Yes.
Okay. So we just refer back to this generally if more polar, okay. Uh, if the electronegativity difference higher, okay, like this one, right? This is 1.4, right? Okay.
So that means it's more ionic.
Yes, it's more ionics. Okay, it's more ionics. Okay, I think we already 11 o'clock. We continue by tomorrow. What time? 8:30 lah. 8:30.